Chapter 5 or Module 5, Magnetic Compass and Direction Systems. We kind of skipped over this subject before. Let's see what further details can we learn from them. Okay, so magnetic compass and direction systems. Starting with Earth's magnetic field basics. The Earth behaves like a large bar magnet with magnetic field lines emerging near the geographic South Pole, correct? And entering near the geographic Northern Pole. So it behaves like a magnet with a South Pole, which is the southern part of the Earth, the southern, the southern pole. And you have the North Pole, that would be the magnetic north of the Earth, to the north all the way to the North Pole, okay? Now, this magnetic field provides the fundamental reference direction for magnetic direction systems used in aircraft navigation, which is very important. Like, it is critical and necessary. You cannot excommunicate that or throw it aside. You have to truly 100% rely on these directional references, especially the magnetic reference, okay? So the magnetic field at any point on the Earth's surface can be resolved into two components. You have the horizontal component, okay, and the vertical component Z. So the magnetic field has two components, the horizontal one, okay, which is parallel to the Earth's surface, and the vertical one, which has to do with altitude, okay? It would be pointing, because you see the magnetic field is, it can change through terrains. And when we talk about the North Pole of the Earth, it's not like a flat surface. You have mountains, you have different things, okay? So the total magnetic field is actually the square root of the square value of the horizontal component and that of the vertical component, which is the theorem of Pythagoras, okay? Pythagoras has provided this theorem. It's like a rectangular triangle, okay, where you have, this is B, okay, and you have the H component, horizontal component here, and the vertical component here. So B is the resulting vector of both. This is how we get it. Now, of course, the angle between the magnetic field and the horizontal plane is known as the magnetic dip angle, or delta. So this is how you get it. Let me draw it a little bit, okay? So you have Z is the vertical component of the field, and H is the horizontal component, correct? So delta, which is the angle called magnetic dip angle between the magnetic field B and the horizontal plane, which is H, okay? This is the angle. So here, the angle delta is the same as here, okay? You know that. Why? Because these two lines, this one and this one, are parallel. Okay, so what is the value of delta? We know tan delta. The tangent of delta is given by the opposite segment, which is H, okay, the value of H, the horizontal field magnitude, divided by, okay, the vertical component of the field, okay, which is Z. So it is the opposing or the opposite segment divided by the adjacent segment. This is how we get tan delta. This is all the way back to the calculus class, okay? So H over Z. So delta would be the arc, or delta would be the arctan of tan delta, okay? So it would be the arctangent of h divided by z. And again, as a reminder to go back to how we got the value of b. So this is the theorem of Pythagoras. You have b squared within the rectangular angle or rectangular triangle, sorry. B squared is equal to h squared plus z squared, correct? So this is b. Here you have is equal to z squared plus h squared. Hence b, which is the magnitude of the magnetic field, is equal to square root of h squared plus z squared. That would give you the final value. Okay, now near the magnetic equator, the horizontal component dominates, while near the magnetic poles, the vertical component becomes more significant. Okay, the variation directly affects the compass behavior. Magnetic compass construction and operation. The magnetic compass is a simple, self-contained direction sensing instrument that senses the direction based on the magnetic field. It requires no external power. This is one of the advantages. So it can operate standalone without any feed, without any external power. It consists of one or more magnetized needles attached to a lightweight compass card, and the needle would rotate to point to the magnetic north. Okay, it's mounted on a low friction pivot, which is necessary so as to guarantee that it would move freely without any drag, because if there's any friction on the axis against the needle might get stuck and not be rotating properly. Now, the compass assembly is enclosed in a fluid-filled bowl, okay, which damps the oscillations and the vibrations and stabilizes the indication, okay? Why? Because without the fluid, the needle might like be turning sideways and increasing the friction, like it might get stuck. Meanwhile, the fluid would guarantee that the needle would have more free movement around its axis, and it would guarantee, or it would prevent it from getting stuck, because it would be a big problem if it was stuck in one position. So that would prevent it from rotating to indicate the corrected heading, okay? And the pilot might go off course due to that needle being stuck in a specific position, okay? So the compass card aligns itself with the horizontal component of the Earth's magnetic field, pointing toward the magnetic north. As the aircraft turns, the compass housing rotates around the magnet assembly, causing the card to appear to move relative to the lubber line, okay? So the card is the one that is moving. Meanwhile, like the needle is always pointing to the north, but with the card moving, it would indicate to you how much you've veered to the right or to the left, and with how many degrees you have moved away from the north, okay? That would determine the heading. So the heading is read at the lubber line, aligned with the aircraft's longitudinal axis. Due to the need for the compass to align with the Earth's magnetic field, it must remain approximately level, okay? Tilting introduces errors when the aircraft tilts, caused by the vertical component of the magnetic field. Compass errors. Despite its simplicity, the magnetic compass is subject to several inherent errors that must be understood by pilots and engineers, both, okay, in order to guarantee a proper operation of the aircraft while accounting for the different excursions from the accurate values that should be reported by the instrument. Correct? So, the magnetic variation, for instance, what is that factor It is the angular difference between the true north, which is the exact north direction that crosses the middle of the North Pole, and that, okay, of the magnetic north, which is the actual vector reported by the instrument due to the field being, in a different direction than the exact north. And why is that? You see, I'm gonna try to display it here. For instance, this is the Earth over here, and by the way, it's tilted. The Earth itself is tilted from its axis. It's not exactly a vertical axis. That is in reference to the horizon that houses most of the planets within the planetary system. So the exact north would be this way, correct? On any direction. However, you have at the center line, okay, you'd have, for example, that would be the magnetic field, okay, but in other areas you have a deviancy of, like, you would have a difference of the magnetic field direction that would veer from the exact north, correct? So if you are close to the center line here, okay, you would have an exact north. Meanwhile, on the sides, for example, here, okay, let's say you are here, the north would be pointing like this. Meanwhile, this is the north that you're interested in, which is the exact north, okay, that is normal or forming a 90 degrees angle with the globe as a reference point. Meanwhile, the north that you would be getting with the instrument is the north pointing to the actual north of the Earth. Okay, I might have mistakenly mentioned it in a different way, that, the perfect north is the north pointing to the center pole. No, not necessarily. The perfect north is the north that is 90 degrees perpendicular to the face of the Earth, to the pole itself, okay? From above and below. That would be the north. In reference to your flight, okay? Not the north like sideways, the perfect north. This is where the correction is needed. So the magnetic variation, let me choose the laser indication, laser pointer. Okay, so magnetic variation is the angular difference between the true north and magnetic north. It varies with geographic location and changes slowly over time due to also the movement of the Earth's magnetic field. Now, the relationship between true heading, the true north, and the magnetic heading, MH, is equal to, true heading is equal to magnetic heading plus the variation, which is the error factor. Okay? Variation is published on aeronautical charts and must be applied when converting between the true heading and the magnetic directions, okay, to guarantee a safe operation of the aircraft. Magnetic deviation, okay, the deviation is the error caused by local magnetic fields within the aircraft, such as electrical wiring, avionics, and ferrous materials, and it varies with heading and is unique to each aircraft. What are we talking about? You see, any electromagnetic field can affect the magnetic field being received by the instrument itself. And how do you get that kind of error or magnetic deviation? Because the aircraft itself houses more than one system. Okay, among these systems, you have the electrical system, where a powered wires are crossing through, and whatever has power going through it, it would create an electromagnetic field which would interfere with the instrument relying on detecting the north magnetic vector for the purpose of assessing or measuring the heading, which is the compass. So the compass would be prone to these deviations that are caused by interference of other electromagnetic fields that are generated by the wiring or other instruments operating close to the heading system, or like the magnetic compass. Among them also, of course, mainly the avionics. Also, you have other factors such as the ferrous materials. Why? Because they can be magnetized and they can affect the magnetic field that's being received by this device, this instrument. So this deviation varies with heading, okay, also, and is unique with each aircraft. Now, deviation is corrected using compensating magnets installed in the compass, okay, in order to apply a correction to the value being read. And these are documented in a deviation card. The corrected relationship becomes MH is equal to CH, okay, plus the deviation. So the magnetic magnetic heading is equal to compass heading plus the deviation factor. Magnetic dip. Magnetic dip occurs because the Earth's magnetic field lines are inclined relatively to the horizontal plane. Okay? Because as we remember, the magnetic field has two components, an horizontal component and a vertical component. The vertical component of the field causes the compass needle to tilt downward towards the magnetic pole. So, if you remember, we mentioned before that the Earth acts as a giant magnet with a north and southern pole. At the north pole, the magnetic field vectors go downward. They penetrate the surface of the Earth at the northern hemisphere, at the northern pole, okay? And at the southern pole, they go outward, okay, to complete this cycle, creating this kind of magnetic fields. So that's why the needle would tilt downward and upward due to or during a turn. Okay, this is where the error comes from. So when the aircraft is within a turn, whether towards the north or the south, okay, it will either resist or so the needle of the compass will either resist the turn, so lagging behind and indicating a value which is lagging behind the actual heading value, or it would be leading the actual heading value, so it would display the value of the heading before the aircraft actually gets there, okay? So it would be preemptive, okay? It would be displaying or indicating a heading which has not, for which the aircraft has not caught up to it yet, okay? Now, so this is when it comes to turning errors. Also, acceleration and deceleration errors implicate some incorrect readings, some incorrect turns of the magnetic, piece within the compass, okay? So the disk would be rotating, would be either leading or lagging during the acceleration, okay? And we're gonna explain why or how it happens. These errors are most pronounced at high altitudes where the vertical magnetic component is the strongest compared to the horizontal component. Let's talk about the turning errors. Okay, so what happens when the aircraft is turning to the north? You see, this would be the aircraft turning to the north, okay? And meanwhile, at the same time, the compass, okay, this displaying disk, or actually it would be a disk, an entire disk. Here, if we consider this rod, okay, the magnetic rod, so to speak, during the north turn, that would be turning downward, okay? It would be executing a down pull. Why? Because this north head has the tendency, okay, to turn towards the north pole, okay? So that's why it would down pull the magnetic piece would be executing or running a down pull, which is against or opposite to the rotation direction, okay, to the direction of or orientation of the rotation of the aircraft, they would be going opposite to each other, okay? Because the north turn is like this, counterclockwise, but the downpour is clockwise. So let's read it. North-seeking end of the magnet, okay, would be pulling downwards. That would be the downpour during the turn, and the downward pull increases during the turn, okay? So the compass will resist the rotation and lags behind the actual heading. So the compass, why? Because the compass is turning opposite to the rotation of the aircraft itself. So it will resist this rotation, okay? And will lag behind the actual heading value. Now, when turning towards the south, what happens is that the turn in such case would have the same orientation, the same rotation heading as the downpour itself. So this will increase the rotation of the magnet. Why? Because you have two forces pulling together, adding up together, and like favoring the rotation or the rotative motion. That's why the compass turns faster than the airplane in such case due to this motion, and it leads the actual heading. So the displayed heading would be ahead of the actual heading in such case, opposite to the first case where you would have a turn towards the north, in which in such case what you would notice is the northern turn being opposite, okay, in an opposite rotative orientation than the downpour. So that would resist the rotation or the motion of the magnet, and the magnet would be lagging. It would be displaying a heading less than the actual heading, okay? It would be lagging behind. Acceleration and turning errors. Now we've already discussed the turning errors and how they affect the magnetic indicator, the magnetic field, or actually, yeah, the magnet that's indicating the heading within the compass, to make it short. Okay, so the compass lags or leads the actual heading depending on the direction of turn that we've discussed earlier. Okay, these affect like the heading, okay, and they are summarized by the mnemonic, okay, accelerate north, decelerate south. As we mentioned before, actually, yeah, accelerate and decelerate, we have not discussed that yet. It has to do with the acceleration and deceleration that we're going to talk about right now. So what happens is that during acceleration, the north-seeking head would be pulled downward, okay? So this would be interpreted by the aircraft as if it is heading or turning towards the north due to the power or due to the forces of inertia, okay? Why? Because the motion, the rotative motion of the needle, compass needle, is affected by a centrifugal force due to the rotation movement. This actually applies both during the turns and during or due to the acceleration, because when you accelerate, the rotation of the magnet around the axis, like the magnetic disk, also accelerates. However, and you have acceleration versus deceleration. So you have during the acceleration, it will turn toward the north. Why? Because this seeking head, okay, the north seeking head would be pulled downwards. Okay, so it would be turned toward the north as if it is like indicating the aircraft is turning towards the north. Meanwhile, during deceleration, okay, and due to the lag, what happens is that the north-seeking head would be pulled to the south, okay? So actually, it would be pushed forward, I'm sorry. It would be, instead of being pulled, it would be lagging forward. It would be pushed forward, so it would start pointing towards the south during the deceleration. So instead of rotating northward, it would rotate southward. Why? Because due to the deceleration motion, as if pointing to the south. So this will be interpreted by the aircraft as if the aircraft is turning towards the south. Again, in acceleration, what happens is that you accelerated, okay, due to that acceleration, the head, the north-seeking head, okay, and its rear, it would be pulled downward, okay, so the north would be pulled upward as if the aircraft is turning towards the north. Meanwhile, in deceleration, it would lag, so it start turning in the opposite direction, and it would seem as if it is pointing to the south, okay, the north head is pointing to, yeah, the head of the needle is pointing to the south, as if the aircraft is turning towards the south. I hope it became clear by now. 5.4 Slaved gyro systems and flux valves. Okay, let's start with the flux valve operation. A flux valve is a remote magnetic field sensor that detects the horizontal component of the Earth's magnetic field. It consists of magnetically permeable cores, okay, wound with electrical coils on the inside arranged to sense or to detect the magnetic field direction. As the aircraft changes heading, the induced voltages in the coils, why? Because by the change or because of the change of the electromagnetic field, you have an induced current. Okay, electromotor force, it is called, which is, if you want to measure it in volt, E, it is indicated or denoted by E equal minus derivative of phi, which is the magnetic field, divided by dt, okay? That would be the change of the magnetic field in respect of time, delta phi divided by delta t, or the derivative of phi, which is the change, the differential, or the change, the shift of the magnetic field in respect of time. This is what gets you E, or the electromotor force, okay? Like the induced voltage due to that shift. So, and this can be detected by this device. Why? Because due to the shift of the magnetic field, we can measure the induced current, okay, in different areas of the plate of the flux valve. As the aircraft changes heading, the induced voltages and the coils vary according to the orientation of the magnetic field. Okay, so V, the voltage, would be proportional to the value of the horizontal magnetic field, which is H, the horizontal component of B, multiplied by cosine theta, which is the angle, okay? That is, in other words, the heading of the aircraft relative to the magnetic north, okay? So if that is the magnetic north, N, okay, and the aircraft is 30 degrees away from the north, that would be theta, okay? And this is the value that will affect the voltage. So by measuring the voltage, we can assess the exact north of the aircraft, the exact heading of the aircraft in respect of the horizontal north. Slaved gyroscopic systems. In slaved gyro systems, a directional gyro provides stable short-term heading information, while the flux valve supplies long-term magnetic reference, just for reference. Okay, so a control unit continuously compares the gyro heading with magnetic heading and applies corrective torques to eliminate the drift, because due to phenomena such as gyroscopic precession that we've discussed earlier, you would have the directional gyro that indicates, that would be calibrated and indicates the heading of north, okay, rotating within the directional gyro equipment. So the gyro itself would start drifting due to the gyroscopic precession, okay? So that's why it needs to be synchronized and continuously updated in reference with the magnetic compass, okay? This is the advantage of the magnetic compass, giving an accurate heading, an accurate orientation towards the north. Now, this combination merges the stability of the gyroscopic system with the long-term accuracy of the Earth's magnetic field, which is very advantageous. Advantages over magnetic compass. Slaved gyro systems eliminate most compass errors, including dip, acceleration, and turning errors. They provide smoother, more stable, more accurate directional information and form the basis of modern navigation system and modern heading systems such as the horizontal situation indicator or HSI, okay, which is part of the attitude indicator. Actually, yeah, it's part of the entire instrument, but this is the HSI. It's like the compass, but something which is more advanced than compass itself. System limitations. Although it is more accurate than a simple magnetic compass, slaved gyro systems remain susceptible to magnetic disturbances themselves. Also electrical failures because they depend on a powered rotation of the gyro, the directional gyro, correct? Which is the gyro part of that instrument, and sensor misalignment. Okay, also you have other errors that are due to, again, mechanical failures within the gyro or the gyroscopic precession. Okay, other phenomena can affect that device, that instrument. So regular calibration and cross-checking remains essential for safe operation. You need to cross-check it with another more reliable instrument. This is why we need redundancy, so that in case it fails, you have another reference for navigation, which is very important.